Trigonometry, Chapter 4, Graphs of the Circular Function, Section 3, Graphs of the Tangent and Cotangent Functions, Video 4, Translations of the Tangent and Cotangent Functions. This series is based on content from Pearson's Trigonometry 12th edition by Lial, Hornsby, Schneider, and Daniels. In the previous video, we investigated functions of the form f of x equals a tangent of bx. The period was pi over b, and the quarter period pi over 4b. The a changes the quarter period behavior to vertical asymptote, negative a, 0, a, vertical asymptote, basically multiplying all the y coordinates by a. The interval of interest changes from negative pi over 2 to pi over 2 to negative pi over 2b, comma, pi over 2b. Basically, the endpoints of the interval of interest got divided by b, just like the period did. And for f of x equals a cotangent of bx, the quarter period behavior was vertical asymptote a0 negative a vertical asymptote, and the interval of interest changes from 0 comma pi to 0 comma pi over b. In this video, we quickly discuss translations of this function. Just as with sine and cosine, the horizontal and vertical translations of tangent are invoked by adding or subtracting values in the function. Specifically, if we had f of x equals d plus a tangent of the quantity b times the quantity x plus or minus c, then the graph of that is the graph of f of x equals a tangent of bx without anything added anywhere, translated as follows. Up if d is greater than 0, down if d is less than 0, left if it's plus c, right if it's minus c. This is exactly what we did with sine and cosine. We played with period and amplitude to create the shape, and then afterwards we threw in the pluses and minuses to move that shape around. Same thing with tangent. Now, instead of doing examples in this PowerPoint, we'll play around with the graph in Desmos. I've already got it set up, so let's take a look at it. Now, what you see currently is the graph of tangent. The function over here has a lot of stuff on it. F of x equals d plus a tangent of b times x minus c. But the way I have the sliders, the parameter set, d and c are both 0, meaning nothing's being added, and a and b are both 1, meaning that the multipliers are just 1, so it collapses to just tangent of x. Now we can verify some of the things that we saw before, such as if we adjust the b, it changes the period. For example, right now the period is you can't tell it based on the asymptotes, based on the labeling of the x-axis. I can fix that real quick. We'll just make these steps of pi over 4. Now you can tell that the asymptotes are pi units apart. But if I change the b from 1 to 2, we'll just put a 2 here, then you'll notice that cut the period in half, because pi divided by 2 is half of pi. But if I change the b to 1/2, then it made the period twice as long. Now the period is 2 pi. So we have the correct period adjustments here. And same thing with the A. We can change the amplitude, and I'll just slide this back and forth. As we do that, you notice the quarter period points get higher according to the A and lower according to the A. And if the A becomes negative, it gets reflected, starts to look like cotangent. But I digress. Let's leave the amplitude at 1, the A at 1 and the B at 1, and let's just play with the D and the C. The D is the number in front, which tells you how far up or down the graph moves. So if you notice, the y coordinates of the quarter period points are being adjusted. Like if I move them up 2, now the quarter period points have 1, 2, and 3 as their y coordinates, which was 2 more than when the D was 0. And I can move it left and right with the C. Now this I have to be a little careful with. I'm going to move the C to the right to make it a greater positive number. And you might be thinking, wait a minute, why is it moving to the right when the C is positive? Because the C is being subtracted. So if C was 2, this would look like negative 2, which means it would move to the right. And of course, if C was like negative 2, then in the function it would be minus negative 2, which is plus 2, which moves it to the left. So everything is still happening as before. So if you were to graph one of these things, like if we wanted to graph, oh, I don't know. Let's say we wanted to graph f of x equals 2 plus 3 tangent of Let's make it 2 parentheses x minus 1. Let's make it x minus pi over 4. There we go. Now we got this hot mess because we have this black graph of tangent running all up in the other graph. So let's turn it off for a moment. If I wanted to get to that graph, the first thing I would do manually, first thing I would do is adjust the amplitude to 3. So my quarter period points are going up and down. Why are they not labeled? They should be labeled. Hmm. 1 second. I gotta figure out what the issue is. I must have deleted something. I found the problem. I tried to define f of x in two different places. On the bottom, I changed it to g of x. But regardless, if we wanted to graph this guy on the bottom, 2 plus 3 tangent of 2 times x minus pi over 4, then we would first adjust the graph to have the correct amplitude of 3, and I use the word amplitude loosely, and the correct period by b is 2 means period be cut in half. So we would get this graph first, and then after that, then we would move it up or down. We would move it up 2 and to the right pi over 4. And I'm going to have to type pi over 4 here because I can't stop right at pi over 4. All right, so adjust the shape, then relocate it, and we should get the exact same graph, which we did. So it's just like any other trig function. Figure out how to stretch it vertically, which changes the quote unquote amplitude, but for the case of tangent, changes the location of the quarter period points. Adjust the period, which is like a horizontal stretch. And then after you've found the shape of the graph, move it up or down according to the translations. So same song, just different verse. There is no try, there is no now you try on this video.